Welcome to the Zero to Advanced Analytics in 90 Minutes or Less TigerGraph workshop. I'm Jeff Tizer, Solution Engineer at TigerGraph, and will be guiding you through a presentation accompanied by a hands-on exercise. I'm joined by my colleague, Vlad Slesarev, who will help field the Q&A. We've had quite a turnout today, and we're grateful you're spending this time with us. The exercise is based on a financial fraud use case and will be executed on TigerGraph Cloud. We'll also be using our PyTigerGraph Python package within a Google Colab notebook. Today's session is packed with content, but the agenda outlining it isn't. First, we're going to set the table with the what, why, when, and how of graphs, graph databases, and graph analytics. With those cognitive utensils in place, we'll then showcase them by creating a TigerGraph instance, loading it with data, and applying some graph analytics to it. First, what are graph databases? Considering graph from a metacognitive perspective, graph is how we think. We form concepts in our mind and link them based on knowledge, experience, and other ways of knowing in order to drive decision making. Now, what are graph databases? There's a lot of content behind this slide, so please bear with me. It contrasts graph databases with relational databases and key value stores, which are representative of NoSQL databases. Now, most of us are familiar with relational databases as they've been the backbone of data management for the last 40 plus years. Among their problems, though, is that they can be designed for OLAP workloads or OLTP workloads, but not for a mix of both. You have to choose at design time. We have a name for this mix at TigerGraph, and we call it HTAP, Hybrid Transactional and Analytical Processing, and we enable it. Concurrent read and write transactions with ACID properties alongside compute and data-intensive analysis and aggregation. So you can have both. In the middle of the slide are key value stores. They're very flexible, but don't scale well and can't adequately represent complex domains. Now, graph databases can represent rich semantics and enable storing, processing, and analyzing highly connected data. What characterizes them is that the relationships between the data are documented and treated as first-class objects. Now, not all graph databases on the market are native graph databases. Some are in fact implemented in key value stores or other NoSQL databases and thus suffer from those platforms' drawbacks. Native graph databases are superior for graph analytics by virtue of their design. Native graph databases consist of vertices, that's the circles over on the right, linked by edges, the lines, to effect what's known as index-free adjacency. Each node knows what other nodes it's connected to, and this enables very fast vertex-to-vertex or multi-hop traversal. As a distributed massively parallel graph database, TigerGraph can perform such multi-hop deep link analytics over billions of vertices and edges in milliseconds. I just mentioned the key elements of graphs, namely vertices and edges. Let me shade in those concepts a bit more in the context of TigerGraph. TigerGraph is what's known as a property graph database. The property graph is a collection of typed vertices connected by typed edges. What I mean by typed is that there's a defined schema for the vertices and edges, such as what you see on the left, customer, supplier, payment, etc. So far, so graph. What makes TigerGraph a property graph, though, is that the vertices and edges can have properties or attributes that describe them, such as the ID, amount, and quantity you see on the right side of the slide. Continuing on our graph journey, let's briefly talk about what we call graph-shaped problems and the when and why of graph databases. Why use graph databases? Well, property graph databases are compelling for many reasons. For one, graphs embrace complexity. They allow you to model a problem domain with high fidelity using just a handful of fundamental key constructs, namely vertices, edges, and their properties. For another, joins have always been the Achilles heel for relational databases. The flexibility you perhaps gain in combining normalized, highly granular data comes at the expense of query performance and complexity. In a graph database, navigation within and among the data is intuitive and thus simple. Finally, graph databases offer natural schema flexibility. It's easy to modify a graph without having to take down the database and or reorganize all of the data. We'll in fact see this in action in our lab. Now, the power of the graph approach is on full display when you employ graph algorithms, which take into account the actual structure and topology of the data, i.e. the graph itself. So here are 7 key data science capabilities powered by TigerGraph. Now, starting on the far left with number 1, we've already talked about deep analytics, but it bears repeating. You can explore deep into your data in real time and discover and analyze connections many hops deep. You can match vertices based on similar patterns of connectivity they have within the graph. Recommender systems work this way. And in graphs, similarity isn't just limited to string similarity, but to structural similarity as well. And we'll see this later in our lab when we look at when we look at one particular similarity metric. With relational commonality and discovery, you start with 2 vertices and fan out from their edges to converge on common vertices. Looking at number 4, a fundamental class of graph algorithms is community detection. These algorithms find latent connections between vertices and detect and classify the communities around them. A common use case here is finding the most influential actors within a network, such as prescribing and referring physicians. Geospatial graph analysis is a common requirement in supply chain use cases. This analysis identifies changes in entities and the relationships with each other as location data. This is useful in understanding the movement of people and goods through a geographic area to identify and address potential bottlenecks in transportation capacity. Time series graph analysis analyzes changes in entities and relationships over time. Such analysis can extend the insights gained from hub detection by uncovering changes in influencer behavior over time to identify compelling trends, let's say. And lastly, machine learning, feature generation, and explainable AI. Graph-based features can be used to train machine learning models, and TigerGraph can enable explainable AI by allowing users to query and understand the results of AI solutions with graph-based features. On this slide and the next, I'll talk about a couple of the capabilities introduced on the former slide. Here we have an illustration of deep leak analytics and relational commonality, 2 of the capabilities on the prior slide, in the context of a transaction between 2 users using a Venmo-like application. User 1 initiates a transaction. Notice that 1 hop from the user, we have all their information such as account number, phone number, and email address, and that the account has a credit card associated with it. There's a direct path from user to transaction, and transactions, such as payments, are executed on a device. A transaction goes from one account to another. This account, in turn, has a user, in this case, user 2. User 2 has attributes just like user 1 and appears to be using multiple devices. On the far right, user 101 is transacting with account 101, which is a known fraudulent account. What we've just shown is essentially a shortest path algorithm between 2 users. Excuse me. Executing this analysis in TigerGraph, there is no joining of tables. The TigerGraph query processor simply walks the edges, finding the shortest path between the 2 vertices. Graph algorithms can be classified into 5 groups depending on what they find or measure. These groups are path, centrality, similarity, community, and classification. In our workshop, we're going to look at representative algorithms in the centrality, similarity, and community groups. We're going to start with one of the most well-known graph algorithms, PageRank. Now, PageRank is a centrality detection algorithm and is used to measure influence in the form of relative importance. The objects of measurement can be web pages, people, or scientific research. PageRank was made famous by Google's founders, but traces its roots to work going back to the 1950s. Now, PageRank has 2 fundamental operating principles illustrated in the lower left. The first is that a page's authority increases if more pages point to it. And the second one is that a page is more authoritative if the pages that point to it are themselves more authoritative. Thus, there's a recursive relationship. Looking at the graph on the right, we can see that Ivy has the highest PageRank score, which in this context means she has the most friends. Now, incidentally, all of our algorithms, including our implementations of PageRank for their different flavors, are open source and can be found over here in our GitHub repository. Okay, and you can see again, they're organized in those 5 categories plus one called Graph and ML. Continuing with PageRank, let's look at an application within financial fraud. It's been shown that users or accounts in it's been shown that users or accounts in financial networks with high PageRank scores tend to be trustworthy. This makes sense because criminals or fraudsters are less likely to transact with authoritative individuals or central nodes in the ecosystem. They tend to lurk on the fringes of the financial system. We can modify PageRank to invert this relationship, though, by positing that people who know criminals are likely to themselves engage in criminal activity. In the graph depicted, bad guy Joe and bad guy Max are known fraudsters, and they're in the red. Running PageRank from their vertices lets us peer into their immediate network community, revealing that Slimy Sam and Suspicious Shelley, who by virtue of their association with these two highly ranked known fraudsters, are themselves highly ranked compared to the lesser ranked, possibly, but probably not, bad people or bad actors. As its name suggests, Jacquard similarity is a similarity measurement algorithm. Jacquard works on sets and measures how similar two sets are based on how many elements they have in common as a fraction of the total number of distinct elements. In other words, set intersection over set union. As the slide shows, in graphs, you can use Jacquard similarity to drive a recommendation engine by recommending products purchased by other customers with a similar purchasing history. Let me spend a little more time on this one. You can see that in basket 1, there's an intersection between, looking at basket 1 and basket 2, there is an intersection of bread and bananas. So there are 2 items out of a total of 7 unique items. And that's a higher score than comparing basket 1 to basket 3, where they only have 1 item in common and a total of 8 distinct items. Rounding out our representative algorithms is label propagation, a fast community detection algorithm. I'm simplifying it a bit, but the algorithm works like this. Each vertex is labeled with a unique community ID. So at first, each vertex is a community of 1. Then repeat the following steps for each vertex until there are no more label updates or the maximum number of iterations is reached. Count the community IDs of its neighbors. Update its community ID to the one most common among its neighbors. In the case of a tie, select a community ID at random. At the end of the process, vertices with the same label belong to the same community. In the slide here, you can see that there are 2 large communities and 2 or 3 smaller ones. We're now going to switch over to setting up an instance of TigerGraph Cloud. So what you'll do is you'll go over to tgcloud.io and click register. Now I've already in fact registered, so I'm going to sign in with Google into my personal account. And you're going to come over to My Solutions, and you're going to click Create Solution. You're then going to click on the anti-fraud group and select fraud and money laundering detection. And then click Next. Go ahead and keep everything at a default. We offer a free tier on AWS, and we'll soon offer free tiers on both Azure and Google Cloud. You can keep, again, everything at its default. Click Next again, and name your solution. I'm going to call mine Fin Fraud JKT2. I'm going to set the initial password to TigerGraph. And the subdomain is essentially the URL to your solution. So I'm going to call it JKT Fin Fraud 2. And you can give an optional description. Click Next. Check that everything looks good and click Submit. Okay. Even though I work for the company, I made a mistake. So let's see what I did here. Subdomain. Oh, let me try hyphens rather than underscores. All right. All right, that's better. So it'll take about 5 minutes or so, but don't go grab that cup of coffee. Stay with me here and we'll continue the presentation. Okay. While our instances are being created, let's have a look at the data model we'll be querying against. As you can see, we have a very simple schema consisting of 5 vertex types: payment instrument, account, transaction, device, token, and user. By definition, transactions occur between 2 parties, which we've modeled as 2 edges connecting the central user vertex to the transaction vertex. One edge represents the sending user and the other is for the receiver. A payment instrument can be something like a debit or credit card or a PayPal account. Transactions are executed using a device represented by the device token vertex. The device could be a mobile phone, a tablet, computer, or ATM. Incidentally, there is a many-to-many relationship between the users and devices. The user can employ many devices, and devices can in turn be employed by many users. Now let's toggle back over to Graph Studio and see if our TigerGraph instance is ready for us. Not quite yet. We'll give it another minute or so. There we go, it's ready. Okay, so let's go into Applications and Graph Studio. Okay. Boom, there we are into the UI. Let me double check my notes here. Okay, all right. So here's what we're going to do next. We're going to view and modify the graph schema. We're going to map and load data. We're going to generate a token that we're going to use to authenticate when we use the Google Colab worksheet. We're going to run some basic queries. We're going to enrich our data set, and then we're going to run some graph algorithms and look at their results. Let's go back to Graph Studio. Okay, so you can see on the left, we've got a logical progression from design schema. So you're going to design your schema. Now, we generated our instances based on a starter kit. So our instances already are seeded with a data set, a data mapping, and a schema. But we're going to modify the schema and modify the mapping and add some queries by virtue of interacting with our Google Colab notebook. So let me show you the schema here. Okay, so this is the schema we're going to start with. All right, we're going to add to it. All right. So we're using the Google Colab. I brought that up. Let me show you what that looks like. And rather than copying and pasting queries over to our instance, we are all going to use Google Colab here to connect to our TigerGraph instances and actually persist some of our queries that we're going to be using over to TigerGraph. It's a much more elegant way of moving queries back and forth, back or over to TigerGraph rather, than copying and pasting from, say, a text pad. Okay. So what we're going to do is we're going to extend the schema by adding a vertex, 2 edges, and a property. So I'm now going to click on the Design Schema tab. We're there. and I am going to switch to the anti-fraud subgraph. So we have this notion of multi-graph. So you can have one global graph and multiple subgraphs that are projections of it that can, well, they're projections of it, but can also have their own vertices, edges, and attribute properties that are unique to them. So I'm going to switch from our global view to the anti-fraud subgraph. And what you're going to see here is it's going to show you that all of these vertices and edges are inherited from the larger multi-graph. Okay. So I'm now going to add a local vertex type. And this again is going to be a vertex that's local to this anti-fraud subgraph only. So I'm going to click add vertex type. I'm going to change the name here to account. And let's change the icon to something a little more interesting. How about asset? And I'm going to add an attribute. Okay, well, actually, first I'm going to declare that the primary ID, I'm going to leave that name and that data type and declare it as an attribute. What that means is that you can actually, whereas it might, if I didn't click the checkbox, the ID would be still act as a primary identifier, but would be invisible to you, and you would not be able to query it as a regular property. Like by clicking as attribute, it's visible to you, and you can query it in your GSQL queries. Okay, so I'm going to add one attribute. Click that. The attribute name is going to be CNT underscore TX, and it is going to be an integer. Okay, we're going to populate this with our transaction count for this user. In other words, it's going to count and store all of the transactions that this user has engaged. And it's an integer, and then I'm going to click the add button. Okay, so I've added a vertex, and now I'm going to add an edge connecting two vertices. Okay, so to do that, I click the edge type, and I'm going to go from user to account, and I'm going to call this edge user to account. Now make sure that you spell it exactly as I do and use well, make sure the spelling is accurate and also the case is accurate, because these column names and these vertex names, these property names, and the edge names are all referred to in the code that we're going to be executing later. And you want to make sure that there is a match between the code and the attributes, the vertices, properties, and edges that refer to them, or that are referred to. Okay. I'm going to make it directed. And that's it. Click add. Okay. And then I'm going to create another one. Okay. Same thing, line icon. And here I'm going to go from account to transaction. And I'm going to call that account to transaction. Okay. I'm not going to make it directed. And I'm going to add a third edge. So I'm going to click add here, and we'll create one more. And this one is going to be from user to user. So it's going to be a recursive edge. I'm going to call it user similar to, and I'm going to assign it a property. Okay. And that's going to be sim score, and it is going to be a float. Okay. With that, I click the checkbox, and now we've modified, let me make this a little nicer, and there, we've modified our schema. Okay. What we have to do now is we have to publish the schema. So I'm going to click the publish button, click continue. It'll take a few moments. I'll go ahead and grab a drink of water. Okay. Let's go back to design scheme here for a second. All right. Now notice when, excuse me, notice when we go to back to the global view, we don't see the edges and vertices that we just added because again, they were local to the subgraph. Okay. We're going to stay here. We're going to add a property to the user vertex. And we're going to call this property PageRank. And we're going to make it a float and click check and publish it. Click continue as before. All right. Now I'm going to go back over to anti-fraud. Well, let's look here and you can see that PageRank is there. Okay. Now, since we added to the global view, we expect to see it inherited into its subgraphs. Let's make sure that happened. So I clicked, toggled over to anti-fraud, float over it, and voila, we see PageRank. All right. Now we're going to map our data over, but we need to make a modification to the mapping that comes with the starter kit to accommodate some of the new vertices that we added. Okay. So I want to point out that this UI is not the only way that you can get data into TigerGraph. And in fact, we are bringing in data through CSVs, but through the UI, through Graph Studio, you can also bring in data from S3 buckets. But we have a lot of other mechanisms to bring data in both batch and real time. Okay. We're just illustrating it through Graph Studio because it's a very compelling and very easy to use integrated development environment. Okay, so we're going to change our mapping here. I'm going to click the map button and we're going to click the client referral CSV and it's going to be used to populate the user to account edge. Okay. And we're going to add a transformation in the middle here. So I'm going to click the Sigma button and we're going to use the GSQL concat function. But you can see here that we have a whole host of other what we call token functions that can do transformations that are typical in ETL and data loading type jobs. So I'm going to stick with GSQL concat. And I, in fact, am going to concatenate 3 properties. So I click add. And we do a very simple mapping. First of all, I'm going to map user UUID over to user here. And then I'm going to use these 3 attributes concatenated to populate the account identifier. So I'll click this, go here, 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 and then finally there. And that is the extent of our mapping change. Okay, there we go. All right, I'm going to publish the mapping. Now that the mapping's all sorted, it's time to load the data. Okay, so we'll go to load data, the next step in our logical progression. Okay. So you can see here that you're going to get statistics for all of the vertices and all the edges, and then each individual vertex and edge. Of course, now everything's empty, and you're going to get a trend showing the progress of the loading. And then you can also get over here, you can get an individual insights into each of the files or the vertices or edges, any of the objects that are being loaded to. So I'm going to press the start load button. I'm going to continue. It's telling me what it's going to do, and we're going to say that's okay. So we'll continue. And this could take maybe a minute or so. Now in production configurations, you can expect to be able to load production configurations where you have a multi-node cluster, you can expect to be able to run tens of thousands to hundreds of thousands of input records per second. And additionally, owing to our data compression algorithms, you can expect, in many cases, to have an aggregate reduction in the persisted data footprint. What that means is that the raw data size might end up being much less when it's stored to TigerGraph owing to our compression technology. All right, we're getting there. We have I think about 5 million vertices total to load and about twice as many edges. We're running on a rather modest EC2 box, so bear with us here as we round out the load. And it looks like we finished at least one load. There's another one, a couple more. Almost there. Bear with me. Okay, I think we're done. Excellent. Let's just give it another pulse. Okay, good. We're asymptotic now. Okay, so let's go ahead and begin to explore the graph. What I'm going to do here is I'm going to just pick a user vertex. So I'll click user here and I'll pick 8192 and click search. And I get my vertex. Not very interesting. But what's really cool is once I double click it, you're going to see it explode out and go out one hop to all of the other vertices that 8192, this user, is related to. So I double click that and voila. Let me go ahead and clean this up a little bit. Yeah, and we can keep doing this. You can see here, it's like a constellation around the user here. We've got several transactions that this user has been a party to. We've got one referral, a relationship between these two users. Here is an account that the user is associated with. And finally, here is a payment instrument. And we would also expect to find a device here as well. So I am going to double click payment 8192P. Okay, now a payment is a kind of transaction, so you'd expect there to be at least one other party on the other side of this payment. Okay, so I'm going to go ahead and click this person, and then we'll see, just like we did for 8192, we'll see all the vertices that they're related to. We can continue doing this on and on. I'm also going to click the payment instrument. Actually, no, I've changed my mind. Sorry about that. We'll just keep it like that. And you can see that we can just keep going and going. Okay, double click this transaction, double click this user, and et cetera, et cetera. So, and we can keep laying it out, and voila. So these are, in a relational database, every time we click, we're doing a join, and we think about it, we'd be joining all of these, this instance or this row to all of these other rows, and doing that for these as well and these. And the more joins you add, the poorer the performance. But here you're not seeing really any degradation in performance as we go multi-hops through our data interactively in real time. All right. So you can see that user-directed exploration is really very simple. Okay, this time we're going to do another interactive exploration, and we'll have the engine find user connections for us. So we're going to hide everything. Okay, and I'm going to pick 5 user vertices. Okay, so I'm going to unclick all, click user, keep 5 here, and click pick vertices. Okay, let me clean this up a little bit. Okay, so here we have our 5 user vertices. Now, what I'm going to do now is I'm going to click Find Connections. So I wanted to find any connections that might exist among these five user vertices. Okay, and again, this you might remember there were over 4 million or 4 billion. I can't remember. Many users, and it's going to find the paths using all of these clues within the other vertex types and edge types to find relationships among these users. Okay, so I'm going to shift click these two users and I'm going to say, please find the connection paths. Okay. And we're going to say, actually, let's find connections using all of these criteria, as I mentioned before. Okay, so based on these shared transactions, I have found a relationship between these two users. But look how many other hops it took to find those. So it's this analysis again is all being done in real time. I'll go ahead and shift click another user here, say find connection paths, and we'll see if there's a relationship. And voila, there is. And what the heck? Let's do the next one and we'll conclude this. Okay. Wow, that was a big one. So you can see how easy it is to do these interactive analyses among incredibly highly connected data. And one way that this path finding is used within financial fraud detection, anti-money laundering analyses, is to find situations where what they call the ultimate beneficiary, where that is to say that a user will kick off a transaction that they will ultimately, maybe through many hops or many layers of laundering, are the ultimate beneficiary of. That's essentially the essence of money laundering. You interject it into a system, and through many intermediaries, it becomes laundered and is routed back to you. And this kind of path detection is a key way that money laundering rings are located within anti-money laundering and financial fraud contexts. Okay, now in order to use the Google Colab, we're going to undertake one quick administrative task. So I'm going to toggle over here to the admin interface, and we're going to create a token. I'm going to call this thin fraud, okay, as I've done before. And I'm going to click plus. And this is going to generate a new secret, okay? And this secret is going to be used when we make a REST API connection through the Google Colab using our TigerGraph Python package. So I'm going to copy that just in case I need it again. I am going to, actually no, use BB edit here and copy it there. Okay. All right, that's really it. So let me go back over to Graph Studio. Okay. And now we're going to toggle over to the Colab here. And we're going to do a couple of things. Okay. So the first couple of cells within this Colab are kind of repeating what we already went through, which is setting up the free instance of our starter kit. And I'm going to go ahead and look at my URI here. Okay, I'm going to copy this whole thing, URL. And you don't want to, no matter what I try, it still seems to pick up the /, but you don't really want that. So make sure that when you go back to the Colab, you don't paste that in. So we're going to paste this. Let's see what I mean? That's okay. And that should be that. And then I'm also going to paste in the token that I just copied. So good thing I copied it over because I replaced my my clipboard with my URL. All right, so let's go ahead and paste that. Okay. So good. Now let's go ahead and click this first fetch packages. Let's get all the packages we need in order to run our interactions here through the Colab. Okay, done that. Now we're going to set up a connection with TigerGraph. Okay, we'll test that connection. Excellent. It did an ls, which is a command a lot like in Unix, where it gives us a list of all of the vertices and edges within the database that we're connected to, which, excuse me, the graph, which is anti-fraud. And we're going to create an API token. So in other words, a connection instance. And now I'm going to, or we are going to run a basic query to see if all is well. And we're going to press this button, and it is going to create a query test in our instance. So let's go over here to write queries and see if in fact we have a query called test. Indeed we do. And I am going to run it in interpreted mode. We have two modes of running queries, interpreted or compiled. Compiling it, all TigerGraph is written from top to bottom in C++. That's one of the reasons why it's so performant. And when you choose to compile a GSQL query, it is compiled into C++ code, which makes it very fast, very performant, and that's recommended for production installations. But we can also interpret it, run it in interpreted mode, because compiling might take a minute or so. And voila, we indeed have our test. So what we've really essentially shown is that we have a good connection between the Google Colab, thanks to the TigerGraph Python package, between this Colab worksheet and our instance of TigerGraph. All right, and we'll just keep going down the line here. I'm going to cheat a little bit in the interest of time, and I'm going to toggle over to an instance I have from now on that already has all of these queries loaded. But we'll run them just the same. Just we'll save a little bit of time on the compiling. As some of these, most of these can be run interpreted, but some of them need to be compiled. So we'll go ahead and we already did that one. Sorry, no, actually, did we do this one? Let's do it again. Just for the heck of it. Okay, so now we have a query called select user. So I'll go over here. What the heck? I said I'd go use my other instance, but that's okay. We'll go to select user. It's a very simple query. We'll interpret this. And it's going to prompt us for a user. You can see here that this is a parameterized query. And I'm going to choose our friend 8192. And we should see, once I double click it, something that looks an awful lot like what we saw when we did the interactive analysis earlier. Make this a little bigger. Okay, so there's certainly more than one way to get data in TigerGraph. There's interactive, there's queries, there's the REST endpoint, and all sorts of other connectivity mechanisms. But what you're seeing here is essentially what we saw when we explored the graph using the Explore Graph element of Graph Studio. Okay, so going back to our Colab, what we have next is to install a more interesting query here, and that is to get not just a single user, but all the user and all of his or her transactions. So we'd press play here, and it would create a query called select user TX. And again, I'm going to go over to my other instance, and here is select user TX. I hope. And what may have happened is that because I haven't used it, this instance timed out. In fact, I think that's what happened. So let me go ahead and quit here. Go back over to Portal. Yep. I'm afraid that my instance here. Oh, it's good. Still, it might. If there's in a period of particular or within a period of inactivity, the instance will stop, and then after that, it will in fact terminate. But luckily, we're still up and running, so I just need to go back into Graph Studio, click Write Queries, and let me go ahead and hide all that. And let me remind myself of which one it was. It was select user TX. So we'll go over here to All right, hold on a second. I see what happened. Okay. It defaulted me to my other instance. I'm now going to log in as TigerGraph account. Apologies for this, but thank you for bearing with me. Okay. So go to my solutions. All right, this is what I was talking about. Okay, not so fast. Let me go ahead and start this. Not to worry, we'll just go over here and we'll continue. So, apologies for the confusion. Having two instances will pay off in a little bit when we're running the more interesting queries. So I'm going to create select user TX. Okay, we're going to find it over here. There it is. And we will do the same thing. We will interpret it. And we're going to find all the user transactions for 8192. Okay. And it looks the same because, in fact, we already double-clicked it and saw the transactions for this user. So that should look very familiar to us. Okay. And we'll continue. Back to the collab. And what we're going to do now is we're going to showcase the accum clause within GSQL, which is a very novel way of doing aggregations in graphs. So we don't have a group by in GSQL. What we have is accum and post-accum, which are much more powerful and much more flexible than the group by. And what we're going to showcase here is that we're going to actually aggregate the transaction amounts, we're going to aggregate the transaction amounts for a given user. So once again, I will create that in my environment. So it's called var trans aggregate, and I will go find that. And there it is. Once again, we will run it in interpreted mode. So we'll pick our friend 8192, run query. And what we should see here, let me make it a little bigger, is that if I hover over, we're going to see a transaction amount of $693. So if we were to look at each of these individual transactions, add them all up, they would total 693. Okay. Let's go back over to here, and then we'll do something that illustrates the post-accum. Okay, and that is to get an average. So there are some operations within GSQL that can be done as the engine is navigating from vertex to vertex over the edges. Okay, and that's the accum. Okay, but there are some some operations that can't be done until the traversal is finished, and that happens in the post-accum phase. For instance, an average. You can only average a handful, or you can only average amounts after you've already got them all in. Okay, so you can't average as you're navigating. You have to wait until all of the edges have been navigated, and then you can then do your averaging. So that is what happens in post-accum. So I will click this. We'll install that query. It's called the var query post-accum. Once again, we'll come over here and we'll find it right there. We'll run it in interpreted mode. 8192 again. And let's make it a little bigger. What we're going to see here, if all went well, is that when I hover over here, we're now going to get the average transaction populated. So if I take 693 divided by the number of transactions, I would get 57. Okay, and that's an illustration of the post-accum keyword within GSQL. Okay, let's see here. Now I want to point out, as we scroll over to our more meaty analyses, that is PageRank, label propagation, and Jacquard, which we talked about earlier, and there was a reason why we talked about them on those prior slides, because I wanted to explain what they were all about, so that when we run them momentarily, you'll know what they're doing. But I did want to point out that all of those interactive schema changes we made could have also been done through DDL. Part of the GSQL language or a subset of the GSQL is our DDL commands, and we could certainly have done all of those changes via DDL commands. But I wanted to show you a bit of Graph Studio, and wanted to have us do them interactively. Okay, but you can see here that everything that we did could also be done via DDL. Okay, so what we do now is, and this is a query that has to be um, compiled. Okay, it can't be interpreted, and so this is where I'm going to cheat a little bit and toggle over to my other environment. But you can go ahead and press the play button here and create it in your environment. Okay, and it's called perform insert enrich, and what it's going to do is it's going to populate one of those edges that we created earlier. Okay, I'm going to toggle over to this environment and pick Graph Studio, go to write queries, and there's perform insert enrich. Okay, let me make sure that, okay, good. Data are loaded, and I'm going to run that query. And once I do that, it is going to populate the, sorry, let me check my notes here. The account to transaction edge. Okay. All right, all done. So what we're going to do now is I'm going to go into Explore Graph, and we're going to, oh, this is kind of a preview of coming attractions. I'm going to go look for our friend 8192 again. Click search. Okay. And I'm going to double click. Okay. And now, when I click the account, what I should see are all of those edges that we just populated. And my colleague Vlad likens these to the firing sequence in the Death Star in Star Wars. And I thought I had a graphic showing that. The resemblance is uncanny, but it was a very keen observation. And you can see what we've done here is by running that last query, it populated all of these edges. Okay, account to transaction edges. All right. So now it's time to run the page rank query. Okay, so you would go over to the Colab and install PageRank. Okay, I've already done that here. We're going to go to Write Queries, and this one has quite a few parameters, so bear with me as we run it. Okay, so B type is user. Excuse me. E type is user refer user. Oops. Gotta be careful there. User refer user. Max change is going to be 0.001. Max iterations is 25. Damping is going to be 0.8. That's the probability of whether or not the random walker that is at kind of the heart of PageRank is going to continue on the walk or is going to teleport to another vertex and start a new walk there. So that is 0.8. We'll say top K is 100. Print to cum will be true. Result attribute is going to be PageRank. That's the attribute we're going to persist PageRank to, and that's the attribute that we added when we distinguish between the attributes that were added on the global global graph versus the subgraph. File path is going to be blank, and display edges is false. So I'm going to run this query. Should just take a second or so. All right. And now we have vertices that have been given PageRank scores. Excellent. So let's go ahead and take a look at two users. You can see that these scores are um, ordered from highest rank to lowest rank. Okay, and we're going to compare and contrast two users, one highly ranked and one less ranked. So we'll go back over to Explore Graph, and I'm going to once again hide the Death Star, and we will pick a couple of users here. I'm going to grab 16988 and 21462. Okay. So you can see here that we've got one has a page rank of 1.352 and one has 1.064. And there is a settings here that you can say, okay, well, for a user or for any of the edges or vertices, here are the properties or attributes that I want to see. So you can see that the reason we're seeing the primary ID and the page rank is because that's what I chose to show. Okay, now here's what we're going to do. Okay, so sorry about that. Okay, so we're going to do the expand from vertices here. And I'm going to expand these relationships just on, yeah. So yours might have all clicked. So what you want to do is unclick all and then choose the user refer user. So we just want to show the connections by the user refer user edge. And we're also going to just select the user. So if in case this is selected, just pick all and pick user. Okay. And we're going to expand from here. And I'm going to make this look a little nicer. Okay. And I'm going to do one more thing here. So what we're looking at is we're looking at all of the for this user. Here are the other users that they're connected to, and then they are, again, all the users have their own PageRank scores, and you can see here we want to look at, well, why is 61988 higher ranked than this one? And intuitively, we can see, and I'll make it a little easier here by toggling off some of the IDs. So let me choose both of those. What we can see here is that there are 4 other users pointing to this user, whereas there are only 3 pointing to this one. And that is the reason for the lower score between the two users. All right, PageRank buttoned up. Let's go ahead and go on to our next algorithm, which is Jacquard similarity. Now you'll recall that Jacquard similarity is an algorithm that determines the similarity of sets as a ratio of their intersection to their union. In our case, the sets are sets of graph vertices representing users, and the criteria for similarity is devices and payments. This algorithm is often used by e-commerce recommendation engines, as I mentioned before, but it can also be used in healthcare settings to recommend next best action based on a patient's healthcare and encounter history. So we'll go over to Colab again, scroll down, find Jacquard similarity, press the play button. It'll be persisted into your TigerGraph environment. We'll come over here, find it. Here, go ahead and install it. And then once it's installed, you'll run it, which we'll do now. So we'll say 10, we'll use 2 million. And sim threshold, we'll say of 0.4, so 40% similarity. We're going to insert an edge. That is how similarity will be persisted, is that we will insert a user similar to edge among all those vertices that meet or exceed that 40% threshold, again, based on devices and transactions. We'll say true. Let's try that again. We'll say true. And number of batches, let's say 10. Right. We're going to run this. And there we go. We can look at it as JSON. We can see the, this is the similarity score here. And we will go ahead and look at it though through the Explore graph, and we'll actually overlay it with our page rank. So instead of saying, let's represent, or let's connect vertices based on user refer user, we'll pick user similar to, and we'll click expand. Make sure everything's highlighted. Yep. Okay. So let's clean this up a little bit and have a look at what we see here. Okay. So you can see that, excuse me, these two users are connected, and their similarity score is represented here. It's an edge property, is 0.8. So they're very, very similar. These users are 0.6. Some of them, as you can see with 0.4, just met the threshold. And yeah, that one too as well. And this one is about 2/3 similar. Okay. So there's a lot more vertices, a lot more similarities, a lot more vertices that are connected to other vertices based on similarity. But again, we just used the PageRank view that we had before and overlaid on top of that. So that is Jacquard. All righty. So moving on to our last algorithm, which is the community detection algorithm label propagation. Now, as I mentioned at this before, at the start of execution, all vertices are given a unique label with label prop. These labels propagate throughout the graph based on their frequency, and in this way, densely connected vertices quickly converge on a label quite rapidly. Because it's parallelizable, label propagation is tailor-made for TigerGraph because of our massively parallel processor architecture. Let's go ahead and look at the code. We'll scroll down to label prop and press play. Once again, go find it in your environment and install it. And we'll go ahead and, before we run it, let's have a look. So once again, what we're doing is we're using so once again, the algorithm starts by every vertex is a community of 1. And what we're doing is we're using our get vertex ID function to label every vertex with its internal identifier. And then as you can see, there's a while loop here, and it's going to end when the max number of iterations that is user specified and it's specified as an input parameter is reached. So you can see here that propagate label, here's a note, propagate labels to neighbors, okay, until they converge or until max iterations is reached, which we mentioned in the slide deck, okay? And then you can see here, we're going to iterate over the map, which is the data structure we're using to get the neighbor label that occurs the most often and assign it, okay? And let's go ahead and have a look. Only iterations, or only parameter is iterations, 10. We'll run it. And go ahead and clean it up again. And what we have here, very interesting visualizations. We have about 7 communities. Now, there were a lot more communities detected, but we have, as part of that query, it said only output those communities that have 7 or more vertices as part of them. And the reason for that is we just didn't want to have the presentation here cluttered. So we've got about 7 densely connected communities, and we'll go ahead and zoom in on one of them. And no surprise there, you can see that most of them, well, all of them are have a similarity score over the threshold. Okay, and these are again very, very densely connected communities. It's a perfect. There are other community detection algorithms, but again, this one is particularly well suited for TigerGraph because it is parallelizable. It's very fast. With that, we are finished with our third and final algorithm. So let's go over here and let's have a recap of what we talked about. All right. So we introduced graphs and graph databases. We distinguish graph databases from the rest of the pack and explain their many advantages, and ended by showcasing the implementation of those three algorithms in TigerGraph. I encourage you to continue using your free TigerGraph instances and having a look at the other starter kits, as well as our test drive site. I've also included a URL to over 80 of our videos, as well as the URL of our certification page. We'd love for you to join the ranks of the Tiger Club. Okay, let's get to the rest of your questions.